Yeah, so what we're going to do today is I'm going to do a simplified version of the tutorial problem. And uh, the idea will be to give you some idea how to use the tools that we've developed. Okay. And that's really what is essential now, because I mean, part of this language of manifolds and so on is giving us tools. Okay, it's a collection of tools that we're going to use to describe curved spaces and curved space times in particular. So we need to understand how to use these tools. Okay, besides just these abstract definitions. Okay, how do you actually use them? Okay, so that's really the purpose of today's tutorial, and it's also the purpose of the tutorial sheets that I shared with you, is to give you that practice for how to use these and to get an intuitive feel for these different mathematical ideas. Okay, so what we'll do first is I'll first work out this one example that I want to do in complete detail, where you'll see all the concepts in action. And then after that, if you have any questions, then I'm happy to answer, and then we can, discuss them. Sorry, questions unrelated to this particular example that I'm doing. If you have questions related to this particular example, of course, feel free to ask questions at any point. Okay. Okay. So we'll start with a simple example. Well, we'll start with R2. Okay. So the manifold itself is R2. And so that means topologically, it's the same as R2. Okay. Now, there are several obvious coordinate choices that we're familiar with on R2, but of course, any coordinate choice is fine, right? Any coordinate choice, any coordinate patch is fine. We'll choose the two coordinate systems that we're familiar with on R2 and just see how these ideas work on the manifold R2. Okay, so we'll use a coordinate patch U. This coordinate patch will be the full R2. Okay, so this is our manifold. The manifold itself is R2. And we'll use the full R2, and then the obvious choice is to use Cartesian coordinates, that is to use an X and a Y coordinate. Okay, so every point is labeled by an X value and a Y value. The second option is to use polar coordinates. Okay, that's another thing that you're familiar with, right? The same point can be labeled instead by talking about its R coordinate and its theta coordinate. So instead of using an XY coordinate, I will use an R theta coordinate. In the language that we're talking about, in this abstract language of manifolds, okay, you should think of R2 as a manifold. Okay, and then we have coordinate patches, and these coordinate patches are locally homeomorphic to R2. Okay, that is, manifolds which are two-dimensional are locally homeomorphic. That is, if I take a coordinate patch, then there's a homeomorphism or a mapping between these points, a continuous mapping between these points and R2. Okay, where since the manifold is two-dimensional. So what we're really doing is, you think of the manifold itself, the original R2, as an abstract quantity. Okay, it's an abstract collection of these points. And the coordinates that we're associating with these points are not really coordinates on the manifold itself. They don't describe, they're not directly the point on the manifold. They're a mapping from the point on the manifold to this pair of numbers. Okay, so it's a slight level of abstraction that we made, which is a separation between the manifold itself and the coordinates that we're putting on this manifold. And similarly, if we can insert the same point, instead of describing it by Cartesian coordinates x, y, we can use a different set of coordinates. So this would be, let's say, phi u, and this is phi v. Okay, there's a coordinate map for the same point. And now, instead of describing it by the real numbers x, y, we're describing it by the numbers r and theta. Okay, so we give it an r coordinate, okay, and a theta coordinate. So this will tell me how much r, how much theta. Okay, so that's what we mean by it's a local mapping to R2. Okay, so the manifold itself is an abstraction. Okay, the coordinates that we choose to put in it are separated from the manifold itself. Okay, they're not they're not actually the points on the manifold. They're coordinates that we, as values that we assign to the points on the manifold due to the homeomorphism between coordinate patches and R2. Okay, is this idea clear? Any questions about this? Okay. So the other thing is that the coordinates assignment has to be unique. Okay, which means that a single point in the manifold, a single point P in the manifold, cannot in the same coordinate system. Okay, so for example, in the XY coordinate system, the same point P cannot have two different XY coordinates. Right? That is, these maps phi u and phi v have to be invertible. Okay, that is, from the coordinates in a coordinate patch, I should be able to recover the point in the manifold. So a single point can only have a single set of coordinates. Okay, so if you use polar coordinates, okay, then you cannot satisfy this for the origin. Okay, that is the point with r is equal to 0. Okay, so r is equal to 0, therefore will not satisfy. Because basically r is equal to 0, there can be many r is equal to 0 points. There can be r is equal to 0 with theta is equal to 0. There can be r is equal to 0 with theta is equal to pi by 2, and so on. All of this really describes the same point. Okay, you can't assign multiple coordinates to the same point, otherwise these maps are not invertible. So therefore, you have to restrict yourself to the domain r greater than 0, which means that if you look at this real plane, okay, the coordinate patch V doesn't cover the whole plane. Okay, the coordinate patch V necessarily has to exclude the origin. Okay, so it's not a full covering of the manifold. Okay, we normally think of it as a full covering, and we understand how to deal with what is happening at r is equal to 0. But strictly speaking, it's not really a full covering of the manifold. Okay, so it's really a coordinate patch that cannot be extended to cover the entire manifold. Okay. So now basically this is what I've shown here in this box picture on the left. Okay, so you have R2, and now a point P is labeled by either an XY coordinate or an R theta coordinate. Okay, and the R theta coordinates don't cover the entire coordinate system. Okay, however, the origin is covered in the XY coordinate system. Okay, it has a unique coordinate 0, 0 in this XY coordinate system. Okay. Okay. Now the other thing is that you need a rule for. Okay, sorry. So, and also these coordinates r theta, r goes from 0 to infinity. Okay, the open 0 infinity, and theta goes from, let's say, you can choose it to be, let's say, minus pi, pi to minus pi, minus pi to pi. Okay, again the open interval. So roughly speaking, it's like all of this. Okay, I have to exclude either. I have to exclude either this region. Sorry. Yeah, okay, there's another subtlety, okay, with these coordinates, and let me just come to that. Okay, so strictly speaking, when we're choosing these open subsets, okay, of the original manifold M as coordinates, okay, you can't map to something like theta is minus pi to pi. You can't go up to pi. Okay, so you can't be in theta belongs to, let's say, left open, right close. Okay, this is not a valid coordinate system. This is not because this is not a map to a valid open subset of R2. So strictly speaking, you need actually two polar coordinate patches to cover R2, even if you exclude the origin. Okay, because even if you exclude the origin, okay, you still have to map to open subsets. So you have to do something like theta is minus pi to pi. Okay, and alternatively, you can do theta belongs to 0 to 2 pi. Okay, and these two together cover the entire space. Okay, this is similar to what we did for the case of a circle, where the first time we took the polar, we used an angle theta to describe the coordinate on a circle. The first time we excluded theta is equal to 0. The next time we excluded theta is equal to pi. Okay, so that's essentially what is needed here. So strictly speaking, you cannot cover the manifold even. So it's not just R2 minus 0. It's, let's say, strictly speaking, the polar coordinates that we're using are over a patch which is R2 minus this patch. Let's see. So where we're excluding all real numbers which are less than 0. So I'll call it R minus, less than or equal to 0. So we're excluding all of these. Okay, so this is the coordinate patch on which our polar coordinates are strictly speaking valid. So this is one choice. Of course, we can choose other choices and get rid of. I mean, move this. Let's say. This particular choice is the one where I've chosen theta belonging to minus pi to pi. Okay, that is, I've excluded theta is equal to pi from this. Okay, in this choice of polar coordinates. All right, so now that we have um, this patch, okay, and we understand what this patch is V, and we understand U. Now what should happen is this: if this is a manifold, then we should be able to first of all write down transition functions, okay, because since you have a manifold M, you should be able to go to its coordinates for any point P. You should be able to find its coordinates. You should be able to invert that coordinate map, get back to the point P, and then you should be able to go to a new set of coordinates, okay, by using phi V. So let's just write that out in full detail. So what we're saying is the coordinates of some point on this manifold, in one coordinate system, we label them by x, y. In polar coordinates, we label them by r theta. And what we're saying is that they are transition functions. Okay, these are transition functions, which tell me what x and y are in terms of r and theta. Okay, so in terms of these maps phi u and phi v, okay, if we are constructing x of r theta and y of r theta, can you tell me what I'm constructing in terms of phi u and phi v?
Phi u compose phi inverse v.
Phi u compose phi v inverse. Good. Phi v inverse takes me from my r theta coordinate back to the point P, and phi u takes me from that to my xy coordinate. Okay, so phi u compose phi v inverse is basically a map from r theta coordinate to xy. Okay, so it's basically these functions. Okay, and now the claim is that these functions have to be C infinity. Okay, if this is a manifold, they have to be infinitely differentiable. Okay, so these maps have to be infinitely differentiable, and you can check that. Okay, so if I now differentiate x with respect to r, okay, keeping theta constant, then I get cos theta. If I differentiate it again with respect to r, then I would get 0. Okay, and obviously if you differentiate more and more times, you'll still get 0. But also I can differentiate arbitrarily number of times. I can, for example, differentiate with respect to theta, keeping r constant. In this case, I would get r sine theta or minus r sine theta. Okay, and I can go on differentiating an infinite number of times. Okay, the result, the derivatives always exist. So these are C infinity transition functions. Okay, that's what we mean by the C infinity transition functions. Okay, so far so good. Okay, so what we've done is basically use the definition of a manifold and the local mapping between a manifold and this R2. Okay, so the important thing is to realize that your polar coordinates are only a coordinate patch. Okay, they don't cover the full R2. Okay, you cannot extend them, in fact, to cover the whole R2. Okay, with this kind of mapping. Okay, so you have to use different coordinate patches if you want to cover up the full R2. So just the coordinate patch V itself, okay, so if I just take the coordinate patch V, okay, with its transition functions phi V, okay, this does not form an atlas. Okay, this by itself does not form an atlas, but U with its coordinate patch phi U, okay, this by itself forms an atlas, okay, because it covers the entire space. And obviously the union of U phi U and V phi V together also is an atlas. Okay, but V phi V by itself is not an atlas. Okay, it doesn't cover the entire space. Okay. Um, okay. Yeah. Now there are many other choices of coordinate systems that you could have chosen. Okay, on R2. Okay, so for example, on this R2, there are many other ways I could have chosen coordinate systems. Okay, for one possibility is I don't have to choose my origin to be at x is 0 or y is 0. I could have chosen my origin to be somewhere else. I could have chosen axis. Let's say I could have used Cartesian coordinates which are rotated. I could have used Cartesian coordinates which are non-oblique axis. That is, I could have used axes which are non-oblique. Okay, I could have used axis like this. Okay, and what I can do is now any point coordinates. Okay, but in any case, at least it's clear that there is a prescription by which you can assign coordinates. Okay, and these coordinates can correspond to all kinds of different ways of taking, finding coordinate systems. One simple way to think about it is if we start with our Cartesian coordinates x, y, okay, and we want to find new coordinates, okay, let's call them u, v, okay, so sorry, some coordinate u and v, and there always have to be two coordinates because we're always mapping to R2, okay, when we're trying to find coordinates, okay, so some open subset of R2. So we want to find such functions, and these functions have to be one-to-one functions, and they have to be C infinity functions, at least in some domain, okay, at least in the domain of validity of the coordinates uv. Okay, so as long as you can satisfy this criteria that you find such functions which are one-to-one and C infinity, then you have a valid coordinate patch. Okay, so you can see that there are many different choices. In fact, the choices don't even have to be linear. Okay, you don't even have to make this mapping linearly. For example, let's say if I have a 1D coordinate system, instead of choosing x, I could have chosen my coordinate to be x square, right? And nothing stops you from doing this. Of course, you see that that now I don't want to choose x all the way from. So if I go from 0 to infinity, this is a one-to-one mapping. If I go from minus infinity to 0, that's also one-to-one mapping. But I can't go from minus infinity to infinity because this is not a one-to-one map. Okay, from x to u will not be a one-to-one map. Therefore, the domain of validity of the coordinate u can only be either 0 to positive numbers or negative x coordinates. It can't be both. Okay, so that tells you what is the range of validity of these coordinates. Okay, as long as you satisfy this one-to-one criteria also. Okay. All right. Sorry. Yes. Sorry. I should also mention that yes, these functions not only have to be C infinity, they also have to, the inverses also have to be C infinity. Okay. That is, if I should be able to write down a function x, y expressed in terms of u, v. Okay. So first of all, the inverse must exist, and the inverse must also be C infinity. Okay. That is a satisfactory condition for the coordinates u, v to describe a valid coordinate patch. Okay. Okay, so this is as far as just putting coordinates on the manifold goes. There are many possible choices. We've just chosen one subset, okay, and we're trying to relate it to the standard ones that we are familiar with, which is Cartesian coordinates and polar coordinates. Okay, and at the moment there is not even a notion of distance measure on this manifold, right? We've not put a metric on this manifold, so we can't really say what the distance is between some point with xy and some point with x plus delta x and y plus delta y. You could choose that distance to be square root of delta x square plus delta y square, but that's a choice. Okay, it's not obvious that I mean, this manifold doesn't come with that prescription for what that distance is. Okay, so now the next thing we'll do is we'll talk about vectors on this manifold. Okay, so here's the idea about vectors. So we defined a vector as we take a curve through the manifold, and at every point P we can look at derivative operators. Okay, and those derivative operators define a directional derivative. And in fact, we use directional derivatives along the coordinate directions as a basis, as a set of basis vectors for describing a vector space, okay, at the point P. So obviously in Cartesian coordinates, okay, our basis vectors at some point will be partial x and partial y. Okay, these will be our derivative operators. So this defines a basis of a vector space at a point P on this R2. Okay. Similarly, instead of choosing partial x and partial y, I could have chosen the basis partial r and partial theta. Okay. This looks a bit strange because we're completely unused to thinking about vectors in this way, right? The way we normally think about a vector in R2 is you take some xy coordinate, you start with this point and you end with this point, and you draw a vector from here to here. Okay, that's what you do. So let's be clear. What do we mean by this idea of let's draw a line from here to here? Okay, when we say we draw a line from here to here and then we're defining this as a vector, so we're doing two things. One is we're picking out a direction. Okay, so this gives us a direction. The second thing that we're doing is picking out a magnitude for this vector. Okay, and this is a displacement vector, obviously, because you're thinking about this vector as being in this space xy itself. Okay, so when you think about the magnitude of this vector, you're thinking about the length between these 2 points. Okay, and the other thing is you're thinking about these 2 points as having a straight line joining them. Okay, so on a general curved manifold or a general manifold, okay, first of all, the concept of a straight line requires you to consider a sequence of many displacements in such a way that the tangent vector remains parallel to itself. That requires you to have a connection. Okay, there is no connection on this manifold at the moment. We've not chosen any particular connection. Okay, you can choose a connection, but there isn't no connection. So the notion of a straight line is not defined. There is no metric, so the notion of a length is not defined. Okay, however, the notion of a direction is defined on this manifold. Okay, there is a notion of a direction, and as we've discussed before, partial r, okay, we didn't show this in class, but partial r you can think of as being in the direction of uh, of uh, of changing r. Okay, so it's roughly in the radial direction. Okay, you can think of it in the radial direction. Partial theta. So if I'm sorry, let me use my coordinates. Okay, so if I'm at this point, I have partial x and partial y. Although these vectors don't live on the manifold itself, they live in a tangent space. Okay, they live in a tangent space. The notion of direction, okay, still is still consistent with what you're familiar with. Okay, the notion of a direction, that is partial x is something which points along the x direction, partial y something which points along the y direction. This is taking a derivative of smooth functions on R2 along the x direction. This is taking a derivative along the y direction. The thing that's not defined is to think about this vector that you're defining, any vector that you're defining at this point. You're not thinking of it, first of all, as a displacement, because displacement would require you to think about a straight line joining 2 points. And secondly, even the notion of a straight line on a curved manifold doesn't make sense, right? Because there's no sense in which you would take 2 points on a sphere and draw a line joining them and think of this as a vector, right? That just doesn't make sense to think about this as a displacement vector. So we want to drop this idea of a straight line connecting 2 points as a vector. Okay, so but that's something that we're already familiar with. Besides displacement vectors, we think about other vectors also on R2. For example, you can imagine that this is physical space. Okay, this is points x, y, let's say in the room. Okay, and at each point you have an electric field. Now, the electric field, the tip of this electric field vector is obviously not pointing to another point in the room. I'm really thinking about the magnitude of this electric field in some space of electric fields, okay, because it has units, right? It has a units of electric field of volts per meter. So it's in a completely different space than the space of coordinates that I'm using. Okay, so similarly, you have to think about these vectors as sort of these abstractions. Okay, they don't live on the space themselves. Okay, they live in a different space, which is the tangent space. Okay, which defines a vector space. Okay, at every point P on the manifold, there's a different vector space. So similarly, there's an electric field, and this electric field can be chosen from many possible electric fields that you can have at a single point. Okay, so the choice of all possible electric fields that you can have at a point gives you is like a tangent space at that point. Okay, and one electric field configuration is picking out a particular tangent vector at every point on this manifold. Okay, at the moment we have not picked out any particular vector. Okay, so we could have picked out some smooth vector field. Okay, so we call this a smooth vector field. Okay, so at the moment what we're looking at is we're looking at one specific point, and we're trying to look at basis vectors of in the tangent space. So the basis vectors are either, you can think of them as partial x and partial y, or partial theta. Okay, and you have to be clear when you say partial, what are you holding constant, right? So here you're holding y constant, here you're holding x constant, here you're holding theta constant, and here you're holding r constant. Okay, now these are basis vectors. Okay, and so what that means is, so now if I have a vector, Okay, so now if I have a vector, okay, so let me just go back to my R2 and let's just draw our, so this is some point which is labeled by either xy or r theta. And let's imagine a vector here, and this vector can be pointing in some direction. And now I have a notion of a partial x direction. This is what I would think of as my x direction, okay, or x hat direction. Although, again, the notion of a unit vector is not well defined. Unit vector means that you have a magnitude for the vector. You're saying it's magnitude 1. We don't have a notion of what the magnitude of this vector is. Okay, we only have a notion of direction at the moment. Okay, so similarly in the y direction, you have partial y. Okay, alternatively, you would say that in the radial direction, I have a partial r, and in the theta direction, I have a partial theta. Okay, so this is one set of basis vectors. This is another set of basis vectors, and what I can do is express one basis in terms of the other basis. Okay, and you'll see that the transformation rule to express these basis vectors in terms of the partial x, partial y basis vectors is exactly the rule that you would expect. Okay, we'll derive the rule first. Okay, so we'll derive the rule and we'll show it's exactly the rule that you would expect under a rotation of these vectors partial x and partial y by an angle theta. Okay, under that rotation by an angle theta, you should recover these partial r and partial y. Okay, but not exactly, because again, we don't really know the relationship between the magnitudes of these vectors. Okay, so roughly intuitively, the direction is you can think of as I want to make a rotation on these two so that it points along the partial r direction, and I would roughly like to make that rotation by an angle theta. Okay, let's see formally in the language that we've developed how to make this translation between these two sets of basis vectors. So partial r can be written as partial x partial r partial x plus partial y partial r partial y. Okay, so here I'm just using the chain rule. Okay, and now this can be written as, so partial x partial r, just remember our coordinate transformation, x is r cos theta, y is r sin theta. Remember again that this translation between these two different bases is only valid in the region of overlap, okay, between the coordinate patches u and v. Okay, so now if I do this, partial x partial r is cos theta, partial y partial r is sin theta. So this is what I get. Okay, this is partial r expressed in the basis of partial x and partial y. Strictly speaking, if I want to express this properly, then I should also express the basis coefficients. Okay, that is, I should express cos theta and sin theta also in terms of x and y. So that is, I should express cos theta as x over r, where that is x over square root x square plus y square. And the sin theta should be expressed as y over square root x square plus y square partial y. So this is correctly now describing the transformation rule to go from these basis vectors in the xy coordinate system to partial r in the new coordinate system. Okay, and similarly, what I would do for partial theta is I would write it as partial x partial theta partial x plus partial y theta partial y. Okay, and again, now I differentiate x with respect to theta, that will give me a minus r sin theta. I'll differentiate y with respect to theta, that will give me an r cosine theta. Okay, so now you see something interesting. Okay, this looks almost like a rotation, except for the fact that there is a factor of r appearing over here. Again, strictly speaking, I should express this r and theta in terms of x and y. Okay, so I should write r sin theta as y, and this I should write as x. Okay, so this will be minus y partial x plus x partial y. Okay, this is strictly speaking the right transformation law, or the right way to write the transformation law. Okay, okay, so now that I have this, okay, I can basically use this transformation law and to write these transformations as a matrix. Okay, so I can write partial r is cos theta sin theta times partial x partial y, and partial theta, okay, is minus sin theta times partial x cos theta times partial y, and I've divided by 1 by r over here. Okay, so what you see is 1 by r times partial theta and partial r. These two together they behave as if it's like a rotation, okay, of partial x and partial y. Okay, this is comforting on one ground, right? On dimensional grounds, theta doesn't have a dimension, r has a dimension. Okay, and so if you assigned, I mean, but again, this notion of dimension, okay, is coming from our notion of thinking about a length. Okay, coordinates can be arbitrary. Okay, coordinates can be arbitrary. So at the moment, okay, when you look at this now, okay, you see partial r, 1 by r, partial theta. You see that really it looks like your new basis vectors, that is partial r and partial theta. If I write this as 1 by r partial theta, then this new basis vector, okay, is related to the old basis vectors, that is partial x and partial y, by just a rotation. Okay, so that's kind of comforting. That's something like a rotation seems to be occurring, except it's a, you know, what to make of this 1 by r. Okay, what to think about the magnitudes of these vectors, that we'll discuss next, and that will only make sense when we introduce the idea of a metric. Okay, and strictly speaking, there's no reason to put this 1 by r here. Partial theta is a perfectly good tangent vector. Okay, partial theta is a perfectly good a basis for a tangent vector. Okay, so now suppose we have any vector, okay, at the point P. This vector can be written, either you can expand it in the x basis, and then it in the xy basis, it has coordinates vx, vy, and it will be something like vx times partial x plus vy times partial y. These are basis vectors. Okay, or you can write it as in the partial r partial theta basis. Okay, so you can write it like this with some coefficients vr and v theta. Okay, and now what you can do is I can relate these basis coefficients. That is, this is the same vector expressed in two different bases. So I can relate the coefficients, that is Vr, V theta, I can relate them to Vx, Vy, or vice versa. Okay, and you can do this, for example, by substituting, you know, by expanding this partial x in terms of partial r and partial theta. Okay, and what you would get is something like this. You get Vx is cos theta Vr minus r sine theta V theta, and Vy is r sine theta Vr plus cos theta V theta. Okay, again, except for this factor of r, okay, it kind of looks like a rotation that you're performing on the Vr V theta coordinates, okay, to get the Vx Vy. Okay, and it's a rotation by minus theta. So let's just write that here. Okay, so I've rotated my basis. Okay, and so my basis coefficients rotate by an angle. If my basis rotates by theta, my basis coefficients will rotate by will appear to rotate by minus theta to keep the vector the same. Okay, so in other words, I have a vector. This is one basis xy. Okay, and then I want to express it in this rotated basis, which is rotated by an angle theta. Okay, which we're calling the r theta basis. Okay, and what you can see is that if I take the components of V, okay, the components of V, the original component of V was this, but what I should do is instead think about rotating V. So if I taken the original vector V, okay, sorry. The original vector V and then rotated it by minus theta. Okay, so I rotate that vector by minus theta. And then I take the components of this, okay, in the original basis, xy basis. That would be the same as writing V in this new basis, okay, where the basis itself is rotated by an angle of plus theta. Okay, I mean, this idea is probably familiar to you, right? It's also something that shows up in quantum mechanics, right? It's a difference between the Schrodinger picture and the Heisenberg picture. You're talking about the same vector, just expressed, either you just change the basis or you change the vector. Okay. Okay, so fine. So now this describes basically how to transform between, you know, between different coordinate systems. Okay, transform vector coefficients between different coordinate systems. Now you can ask about dual vectors. Okay, and for dual vectors you have a dual basis. So the dual basis in the r theta basis is dr d theta and dx dy. Okay, So this is in the U basis, this is in the V basis. Okay, so now again you can find the relationship between them. You can use the law that we had worked out. So which is d. So supposing I have d y mu. Okay, it's partial y prime nu partial x mu. Sorry, dx. Um, sorry. Okay, this was the rule that we worked out for dual vectors. Okay, so just remember the rule, right? The y has to show up here and the x shows up here. Okay, roughly speaking, okay, one intuitive way to remember this is in every coordinate system, right? You can change the dimensions of the coordinates, and dimensionally, okay, the y coordinates, whatever their dimension is, that has to be balanced on both sides, and the x coordinates, their dimension has to balance on both sides. Okay, that's one way you can sort of imagine why this transform has to be in this way. The second thing is you're expanding in an dx new basis. Okay, and so therefore this free index here, okay, will be the free index mu on the right hand side will be on this y over here. Okay, and this partial x nu will this will be a repeated index. Okay, which is sound. So now we can apply this rule to get, so this y coordinates could be the xy coordinate system. Okay, and the x coordinates we think of as our theta r coordinate system. Okay, and we want to find the transformation rule between them. So I've just written what those transformation coefficients are: partial x, partial r. Okay, so you can think of this now as a matrix. For every value of mu and nu, this defines a matrix: partial x, partial r, partial x, partial theta, partial y, partial r, partial y, partial theta. Okay, and so on, and so you can again work these out, and you will get this kind of transformation matrix. So once again, it looks like a rotation matrix. If I pull this r into the d theta, okay, I get something like dx dy is this. Okay, and so let's just compare this with the transformation rule that we had for the dual vectors. Sorry, with the rule for vectors. So for vectors, it looked like this: partial x is a rotation matrix with minus theta. Okay, so if the theta, whatever the sign of theta here is, that's how I'll refer to the sign. So it's a rotation matrix with minus theta, partial r, partial theta. And again, you know, really I thought about this as putting the one by r here. Okay, and similarly, I can think about this, and this is also exactly the same transformation rule, r minus theta. It just happens to be exactly the same transformation rule in this case. It doesn't always have to be the same transformation rule. Okay. And indeed it's not, right? Because you've seen that here it's r d theta. Okay, it's r d theta, and previously you had 1 by r partial theta. So in terms of whatever I had chosen as my original basis vectors, my original basis vectors were actually this. Okay, and there my transformation matrix had an sorry, where do I write the r? So if I move this r back, okay, it's minus 1 by r over here. And similarly over here, okay, if I move the r back, then it appears as r rather than 1 by r. Okay, so it's not the same transformation matrix. Okay, if I'm careful about which basis I'm using. Okay, if I use the coordinate basis, that is. Okay. All right, any questions at this point about these transformation rules for dual basis vectors, vector basis, and so on? Is this okay? Is this obvious, or?
Sir, if we are using coordinate basis, then the transformation for the vector components will always be equal to the dual basis transformation, right?
It's
Like,
not equal, right? We just showed it's not
sir,
equal.
sir, sir, but shouldn't like the Jacobian coefficients are the same? Like I'm not able to understand why it comes out to be different. No, sir, I'm
Like,
talking about the like for vector components and the basis sorry, like reverse, like the basis transformation and the vector coefficients, not the vector basis and the dual vector basis.
this one, yeah, it'll be inverse Jacobian. So for the vector coefficients versus the basis transformation coefficients, this, sorry, did I get inverse Jacobian or the same Jacobian? Sorry, you're right. I got the same Jacobian. No, that's also not right. Um, right, so you basically expand V, right? So V is in one basis, it's, let's say this. In another basis, it's V prime. Okay, and if I want to relate them to each other.
Sir, no, I understood this part. I'm talking about like the dual basis and like
This one.
yeah, yes, sir. Sir, if V mu like the vector components transform via Jacobian matrix J, then so will the
Okay. So
basis, right?
what you're saying is these coefficients of the vector coefficient transformation
Yeah, yeah,
is the
that should be
same as
equal to
the
the
dual basis vector transformation.
yes.
Yes, that I think
Sir,
is
I
true.
think yeah, the R should be in the cos theta term for the vector transformation written above. R cos.
Here, no, it's not. It's always with the sine theta. Oh, sorry. You mean in the second one?
Yes, sir.
Yeah, sorry, you're absolutely right. And the second one is with the sine. Yeah, you're right about that. Yeah, good. Thanks for pointing that out. Okay. All right, so now what we'll do is finally we'll come to the intuitive notion which you're used to, and that intuitive notion, basically the connection is made once you choose a metric on R2. Okay, so the choice of metric will be to choose this two form, okay, for G, the metric. So we'll choose the Euclidean metric, and the Euclidean metric is basically dx, dx inner product dx plus dy inner product dy. Okay, and now this same thing we can now express using so once we make this choice, okay, we can express this in terms of the dual basis of dr and d theta. Okay, so in general, we'll have terms like this. And this, okay. So you can work out this transformation law using this. Okay, so this is a dual basis vector expressed in terms of dr and d theta. And it's quite easy to convince yourself that what you will get is dr inner product dr plus r squared d theta. Okay, so these cross terms just cancel out. Okay, so you don't get any cross terms. So you have to expand dy, okay, in terms of dr and d theta, and similarly expand dx in terms of dr and d theta. Okay, and what you will get is this. Okay, so the same g is now expressed. It's a single tensor, just like we had previously a single vector expressed in two different bases. This is a single tensor, a 0-2 tensor expressed in two different bases. Okay, it's expressed in the xy coordinate basis, and this is expressed in the v coordinate basis. Again, the map between these two is only valid in the overlap region between the two coordinate patches. Okay, it's not valid outside that patch. Okay, so now what we can do is, now let's think about the notion of displacement, right? Previously we were talking about vectors, and we're talking about this notion of displacement, right? And at least we would like the notion of infinitesimal displacement. So instead of displacing by a finite amount, at least some infinitesimal displacement where I change the coordinates by some amount dx. Okay, this dx is not the same, even though we use the same notation, unfortunately and confusingly. This dx is not the same as this dx. Okay, even if I read this as a small dx, it's different from the dx that we're using here. This is a dual vector basis. This dx is a small displacement. Okay, because there is a subtle relationship between them, that's why we use them. Okay, but let's not worry about it. So it's dx times partial x plus dy times partial y. Okay, so I want to displace by an amount dx dy. Okay, I want to displace my coordinate by an amount dx to dy, or this vector is basically an infinitesimal displacement vector. Okay, and in the r theta coordinates, I can write it as a dr displacement and a d theta displacement, where dr is related to xy in the usual way. Okay, since this is an infinitesimal displacement in dr, I can really write this by writing infinitesimal displacements in the x and y directions. Okay, so or rather the other way, it's easier to relate them the other way. So dx, okay, will be dr cos theta plus r times minus sine theta d theta. Okay, here this is really differential, so they're small displacements. So you can really relate a small displacement in xy to a small displacement in r theta. Okay, it turns out that this rule is the same as the rule that we found here for the dual vectors. Okay. Okay. Okay, but here really you think of these as small displacements. Okay, and now what we do is we plug in these. Sorry. Now what we'll do is now we'll try to find the metric acting on these small displacements. Okay, so we'll find g acting on vv, and that is what we'll call ds square, which is the line element. Okay, so this is the line element. So once we have a small displacement vector, we can use that to find the line element, and that's easy to see what that would be, right? So now if I look in the x, I can calculate this in two different ways. I can calculate first in the xy basis, and then I can calculate in the r theta basis. In the xy basis, when I calculate, this dual vector acts on, from the first v, it acts on partial x, okay, and pulls out the coefficient dx. In the second, on the second v, this dx acts and acts on the partial x of the second v, and it again pulls out the coefficient dx. So I get a dx square. And now I get a plus dy tensor dy, okay? And again, similarly, acting on this vector twice, I would get dy square, okay? And it would be plus dy square from this plus. Okay, so the line element would just be the standard line element that you would expect. So now you've associated, given this metric, okay, g, you've now associated a length with that displacement, okay, or a finite size with that displacement, and that size is dx square plus dy square. This is usually what we think of as our Euclidean displacement. Okay, so we've now assigned a length scale to these coordinates. Okay, and similarly, you can work this out for in terms of this now dr. So I could have exactly worked out the same GVV, okay, using the r theta coordinate system. The result should be exactly the same. Okay, so I applied dr wedge dr, okay, on v twice. So the first time I pick out dr square. The second time I pick out the r square is pulled out, okay, and I get a d theta square. Okay, and you can check, of course, that even with this rule for this infinitesimal dx and dr, dx square plus dy square can obviously be expressed as dr square plus r square d theta square. Okay, so this is your standard displacement. This is either expressed in Cartesian coordinates as dx square plus dy square, or in polar coordinates as dr square plus r square d theta square. Okay, now what you can do, and we'll do this often in this course, is you can write a general g in terms of basis coefficients times dx mu wedge dx nu. And you can think of this g mu nu as a matrix. The size of this matrix is n by n, where the dimension of the manifold is n, because these mu take n coordinates, nu takes n values. Okay, so for a two-dimensional manifold, our g mu nu Cartesian looks like this. It's just 1, 1, 0, 0. For our G mu nu polar, it looks like this. It looks like 1, 0, 0 r square, okay, which is what I got from here. Okay, this is different from the G mu nu, G upper mu nu. Okay, G upper mu nu is by definition the inverse of this matrix. Okay, it's the inverse of this matrix, and you have to be careful where what the mu and nu indices refer to. Okay, so the way I'm writing it, I have to be careful about my ordering of bases. So my ordering of bases is this is x and this is y. Okay, and similarly this is x and this is y. And over here in polar coordinates, this is r and this is theta, and or if you like, this is partial r and partial theta. And similarly, this is partial r and this is partial theta. Okay, or better yet, to think about it in terms of dual vectors. Sorry, so think about this in terms of dx dy. Okay, and this is dx dy. This is how I take the inner product of G. I can write it in matrix notation. Okay, this GVV. Okay, or sorry, if I want to construct the tensor G. Sorry, if I want to construct the line element, let's do the line element. That's simpler. So if I want to construct this G line element, I will use the displacements dx dy. Okay, times this matrix G times dx dy. Okay, that will give me the line element. So you have to be clear what is the ordering of these bases. Okay, when I write down this matrix for G. So and now when I take the inverse of G, okay, when I take the inverse of this matrix, I will write it like this. Okay, so again, I'm here thinking about this in the same basis, okay, in the same ordering of the basis, but now I'm thinking about the inverse matrix, which I'll denote with the G upper mu nu as 1, 0, 0, 1, and the inverse of G mu nu in polar coordinates is 1, 0, 0, 1 by r square. Okay, so in particular, if I want to pick out this entry, this 1 by r square, this I will denote as G theta theta. Okay, this is the theta theta entry of this matrix. The first coordinate is the GRR coordinate. This entry is the GR theta, and this entry is the G theta R coordinate. Okay, and since G is a symmetric matrix, okay, since it's a defining property of the matrix that we're choosing, GR theta is equal to G theta R. So G will always be a symmetric matrix. Okay, a real symmetric matrix. Okay. Okay, and finally now we'll come to the idea of dot products of four vectors. So if we have two four vectors, v and w, which in components can be expressed as, let's say for example, v is equal to vx partial x plus vy partial y, or alternatively in polar coordinates as vr partial r plus v theta partial theta. Now that you have a metric, now you can finally define this inner product. Okay, now you can finally define this inner product, okay, on these two vectors. And what you'd get in Cartesian coordinates, you just get this. Okay, and this looks like your standard dot product that you would get. In polar coordinates, you'd get something slightly different. Okay, because the metric is 1, 0, 0 r square. Okay, so what you get is vr wr v theta w theta r square. Okay, this is what you get. Okay, you can use the rule that we found to relate vr in terms of vx vy, v theta in terms of vx vy, wr in terms of wx wy, and w theta in terms of wx wy, and you can check that these two are exactly the same expression. Okay, this quantity is coordinate independent. Okay, the quantity that you evaluate is coordinate independent. You can evaluate it using different coordinate bases, but the result that you get will be exactly the same. This dot product is independent, defined independently of your coordinate choice. Okay. Okay. Now the other thing is, we talked about dual vectors, and once you have a metric, okay, the dual vectors are related by an isomorphism. Okay, so that is, if I have a dual vector v star, which I write as some v star mu dx mu, then I can define an isomorphism between this dual vector, okay, and a vector v, okay, through their coordinates by writing it like this. Okay, so I can write these dual vector coefficients in terms of the metric and v nu. Okay, and when I do this, I will relate I will find dual vector coefficients vx star, vy star, which are basically just vx and vy, and this is because the metric g mu nu is 1 1 in 0 0 in Cartesian coordinates. In polar coordinates, okay, Vr star, the dual vector component Vr star would be Vr, but V theta star would be R square times V theta, because in polar coordinates, the metric is this. Okay, so this would be the G theta theta component. Okay, that's what gives me V theta star. Okay, so this idea of dual vectors is unfamiliar to you. Okay, and we'll see why. Okay. So this is the rules, and now we'll try to relate all of this. Okay, what we found about vectors and dual vectors, we'll try to find related to our usual notion of 2D vectors. Okay, so usually when we try to write down 2D vectors, we'll write down Vx x hat plus Vy y hat. Right, this is what we would try to do. Okay, or in polar coordinates, we would write a vector v, okay, as some vr in the r hat direction plus, okay, so let me call this the usual one. Okay, so this is the usual thing that we would write down. Okay, some vector components vu in the theta hat direction. So this is the usual way in which we write down vectors. Okay, so what is the relationship between this usual way of writing down vectors and the vectors that we are writing down? Okay, well, what we have to do is essentially what we're defining. So for example, let's take the case where, let's take a simple case where the vector points, let's say, only along the y direction. Okay, so if it's only pointing along the y direction, then our vector is vyu y hat. Okay, in Cartesian coordinates. What do we mean by this? We mean by this that it points in the y hat direction and it has a magnitude which is vyu. How is that magnitude defined? The magnitude is actually defined when you have a metric. Okay, so in our notation, our vectors are defined as some vx partial partial x plus vy partial partial y. Once I tell you that the metric is 1 1 0 0, okay, the magnitude of this vector gets fixed. Okay, the magnitude of this vector is square root of gvv, which is vx square plus vy square square root. Okay, this agrees with the notion of magnitude of the vector expressed using these standard Cartesian coordinates. Okay, so in this case, basically our vx is the same as the vx usual, our vy is the same as the vy usual for this choice of metric. Okay, for this choice of metric in Cartesian coordinates, these are the same. Okay, if for example I had scaled my g coordinate, so instead of 1 1, I had chosen, let's say, some scaling over here. Okay, so I choose some parameter b. Then my metric would not be vx square plus vy square. It would rather be vx square b square plus y square. This is what I would get when I took the dot product of v with itself. Okay, because I have to insert this metric here. So now if I want to relate it to, in the usual way of thinking about what the magnitude of this vector is, I would say that the norm is vx usual square plus vy usual square. Okay, and so what I see is that I can make an identification. Okay, I can make an identification that vx usual is whatever I'm calling vx times this b. Okay, and sorry, I should put a b square here. Okay, and vy usual is just vy. Okay, there's no factor of b that appears over there. Okay, and so what this b is it's really a measure of how I'm scaling my distance, right? Because my infinitesimal distance, I'm saying, is not dx square plus dy square anymore. If I choose this metric, what I'm saying is now my infinitesimal measure of distance is b square dx square plus dy square. Okay, that is, if I move 1 unit in dy, that is equivalent to moving 1 by b units in dx. Okay, or alternatively, 1 unit of dx is equal to b units of dy. Okay, they'll both give me the same distance measure. So the metric really is giving you that information about the distance measures, okay, and it's relating them to your coordinates. Okay. So finally, let's make the connection now for polar coordinates. Okay, so with this understanding, okay, we can now apply this to polar coordinates. So our usual way of writing this vector is VU r hat plus VU theta theta hat. And in the approach that we are doing, we would write this as VR partial partial r plus V theta partial partial theta. Okay. The magnitude of this vector in our usual way, I mean, in the usual way, we would think about it as VU r square plus VU theta square. The magnitude of this vector, we have to use the metric for, okay, and we would write the magnitude as VR square plus V theta, sorry, but not plus V theta square, because the metric in polar coordinates is 1 r square. Okay, so we have to put a V square theta, V theta square r square. So this is the magnitude of V. So now if I want to relate these two things, okay, then I would identify the usual V, okay, with VR, but the usual V theta, okay, is not V theta, this V theta. Okay, so the usual V theta is equal to R times this V theta that we have, okay, over here. And it's easy to understand what is going on, okay? When we are defining these basis vectors, okay, these basis vectors have a sense of direction, but not a sense of magnitude. Once we assign a sense of magnitude, okay, once we assign a sense of magnitude, it is not partial partial theta that has unit magnitude. It's 1 by r partial partial theta that is a unit vector in the theta direction. Okay, so this is a unit vector in the theta direction. This has unit magnitude. Okay, you can easily see this because if I take g theta theta, 1 by r partial partial theta, 1 by r partial partial theta. Okay, or if I want the magnitude of this, so I'll remove this. You can think of this as what I'm doing is I'm taking the action of g on this unit, on this vector. Okay, and what I will get is g theta theta times 1 by r square. G theta theta is r square. This is 1. So this is a unit vector. Okay, it's a unit vector because now I have a metric by which I can measure magnitudes. Okay, without that metric, there is no way to associate a distance with any of these. So indeed, when we're writing down something like r hat and theta hat, we already have a notion of distance that we're thinking of. But the concept of directional derivatives, okay, as defining a basis for a vector space is much more powerful than that. Because the directional derivatives themselves as being a basis for a vector space doesn't rely on having a metric. If I have a metric, great, I can find out the magnitudes of these vectors. If I don't, these vectors still exist and I have a way to define them. Okay, that is why this notion of how to talk about vectors is much more powerful as an abstraction than what we're used to when we think about vectors in R2 or R3. Okay. Moreover, this idea is so powerful that it even generalizes to curved spaces, because on a curved space, there is no way I can even I know it to even talk about what the magnitude of a vector is. Here I'm just using curvilinear coordinates on Cartesian space, okay, with this Euclidean metric. But on a genuinely curved space, okay, like the surface of a sphere, okay, how do I define a vector on the sphere? Okay, of course I can define a direction by thinking about the tangent to that sphere, but how do I define a magnitude? How do I define distances? Okay, all of these things only make sense once you start going through the natural progression of talking about vectors on manifolds, and then you assign a metric to the space. Okay, so these concepts are much more general and they apply to spaces which are non-Cartesian. And I don't even have to think about the sphere as being embedded in some higher dimensional space. They naturally tell me about vector spaces on the sphere itself by thinking about curves on the sphere. Okay, so you don't even have to rely on embedding to think about these vectors. Okay, that's the power of this approach. Okay. Now we'll come to the idea of parallel transport. Any questions here? I'll pause and you can just tell me if you. Okay, is this all familiar to you? I mean, have you tried the tutorial sheet and have you seen these ideas in action?
Yes, sir. Sir, I had one doubt. Like when we are asked to find smoothness of functions or components of a vector field, we just need to ascertain that every order of partial derivative is well defined, right?
Yeah, exactly. I mean that is what we mean by smoothness.
Oh.
Okay. All right. So now let's come to the idea of Levi-Civita connection. Okay. So we won't talk about connections, the general choice of connections that you can have on a manifold. Okay. We'll talk about the specific choice that you get for a connection. And remember, a connection is something that allows you to, on a general manifold, if I have a vector space here and a vector space here, these vectors are a priori unrelated, or the vector spaces are unrelated. Okay, but if I want to compare vectors at two different points, I need to parallelly transport from one place to another. The thing that allows me to parallelly transport a vector from one place to another is the connection. Okay, and we've seen that there are many possible choices of a connection, but once you have a metric on the manifold, then you get a unique choice. Okay, well, up to some caveats, which is that you don't have torsion. So if you don't have torsion, okay, that is if this metric connection is symmetric in its lower two indices, then you get this unique connection called the Levi-Civita connection, okay, or it's also called a Christoffel symbol. Okay, so this Christoffel symbol, which we'll call gamma, this is a special gamma which is picked out by the metric, is this. Okay, this is the formula that we worked out in the last class. So here this is the inverse metric, okay, G lambda rho, partial mu G rho nu. Okay, so the free indices are lambda mu nu and rho is summed over. Okay, and you should try to remember this formula, even though you won't be required to remember it for the midsem, but you should try to remember this formula and I'll tell you how to remember it. So this free index appears over here. Okay, then there's a repeated index. So what is in the inverse matrix looks like this. Then there's a partial mu. Okay, so this is the first index here, G rho nu. Okay, so every time what we're going to do is we'll have G factors of a derivative and a G. Okay, so everything inside this bracket is a derivative and a G. In the first term and the second term, what we'll do is we will take the derivative with respect to first the mu or with respect to the nu. Okay, and then what we will do is in these two terms, okay, so wherever we took out the, so you can think about G mu nu, and where I'll take out the first index and I'll replace that by a rho. Okay, so that's G rho nu. And here I think about replacing the second index by rho, okay, which is the repeated index over here. So I get G mu rho. And so these two appear with the same sign, they appear with the plus sign. And now finally what we can do is instead of taking a derivative with respect to mu or nu, we can now take a derivative with respect to this index rho, which is the summed index. So minus, and this appears with a minus sign. So minus partial rho G mu nu. Okay, so let me just undo these annotations. Okay, sorry, it's easier probably to erase. Okay, so now that we have this this Levi-Civita connection, now we can work this out in different coordinate systems. Okay, so in our Cartesian coordinate system, now G rho nu, any entry of G we saw in the Cartesian coordinates, G mu nu was 1 1 0 0. So the entries of this matrix were coordinate independent. Okay, which means when I take derivatives of them, they will all be 0. Okay, because these are derivatives with respect to subspatial coordinate. So all in the Cartesian coordinates, all the possible Christoffel symbols, that is, I can choose any lambda, I can choose from xy, and mu nu I can choose from xy. So these are the possible Christoffel symbols. Okay, there might be a few more that I missed, but all of them will be 0 because whenever I act with the derivative on g, I will get 0. So in Cartesian coordinates, okay, you actually get all the Christoffel symbols to be 0. Okay. Um, in fact, this is the hallmark of sort of flat spacetime or flat spaces, is that there is always at least one coordinate system, okay, in which all the Christoffel symbols vanish. Okay. Um, okay. Okay, so now you can do the same thing in polar coordinates. Okay, in polar coordinates, we've seen that our metric looks like this. It looks like 1r square. Okay, and now this is clearly coordinate dependent. Okay, but it only depends on r. It doesn't depend on theta. Okay, so so now we can try to work out a few Christoffel symbols in polar coordinates. So for example, we could work out gamma r r r. Okay, so let's write down what it is. I can write down half g. And then there's an r over here. Okay, so I use the r here, and now I have a repeated index, which means this index can be an r or it can be a theta. So first let's write down the inverse matrix G mu nu because we're evaluating inverse matrix elements. So the inverse matrix is 1 by r square 0 0. Okay, now this inverse matrix, it has 0 off diagonal components, which means the entries g r theta and g theta r are 0. Okay. So what that means is there's no point evaluating g r theta. Okay, so in that repeated index sum, only the term where this rho is equal to r will survive. Okay, so I'll just take g r r. So I'm just taking the single term instead of a summation over rho. I'm just taking out the term with rho is equal to r. Okay, so that simplifies things. And so now I have, so now you can see that since all these indices, because I'm working out with mu and nu is equal to r, all the indices will be r. Okay, so everything is r. But now you see that this is the derivative of GRR with respect to r. And GRR is 1. Okay, GRR is just 1. It's only G theta theta that is non-zero. Okay, that is coordinate dependent. Okay, so this will be 0. So gamma r in polar coordinates is 0. But now you have an idea of which Christoffel symbol may be non-zero. Okay, and the Christoffel symbol that may be non-zero is the one where you take a derivative of g theta theta with respect to r. Okay, so you're using the fact that only g theta theta depends on coordinates, and we want terms inside the Christoffel symbol where there's a derivative with respect to g theta theta. Okay, so if you think about the structure of the Christoffel symbol, okay, in each term you have the lower indices mu nu. Okay, you have the lower indices mu nu, and you have the repeated index rho. Okay, so you can either have okay, so let's just work out a few. So for example, let's just work out gamma r theta theta. Okay, you'll get half GRR again because the upper index is r. It only makes sense to use the other index also to be r. And now you'll have terms which are kind of interesting, right? Because you'll have terms like partial theta gr theta, partial theta g theta r. Okay, this is basically coming from replacing one of these thetas by r. Okay, and pulling the other theta index outside to take a derivative. Minus partial r. So now I take the derivative with respect to this repeated index g theta theta. Okay, and this is what we're after, right? This is the kind of term which we know will be non-zero. So partial r g theta theta, this g theta theta is r square. So this will be 2r. So what I get now is this is minus 2r. Okay, GRR is 1 and this is half. So minus half times 2 half times minus 2r is minus r. Okay, so I get gamma r theta theta. So this is a non-trivial connection, which I get is minus r. And similarly, I get I can work out this symbol. Okay, gamma theta r theta, which is half g theta theta. Okay, so now because I'm using theta here, I get theta here. Again, I'll only evaluate g theta theta. I won't evaluate terms like g theta r because those are 0. And then I have partial r g theta theta. Okay, so now I've replaced the first index here by the repeated index theta, and I've taken the derivative with respect to this index, which is partial r g theta theta. I also have terms like partial theta gr theta minus partial theta gr theta. These are anyway 0 because gr theta is 0. But again, you see that I get this partial r g theta theta type term, okay, which is non-zero. That is 2r. Okay, and here it appears with a plus sign. And g theta theta is 1 by r square, and there's a factor of half. So the net result is I get 1 by r. Okay, and by symmetry, okay, our Christoffel symbols are chosen such that gamma theta theta r is also the same. So we'll also get 1 by r. So you don't have to actually work out all the Christoffel symbols. Sometimes symmetry can tell you which ones are non-zero and how to compute the others also. Okay. Okay, so I won't do this, but you should try this out. Okay, is under parallel transport. Okay, if you have a vector v, which is expressed as vr partial partial r plus v theta partial partial theta, or it's expressed as vx partial partial x plus vy partial partial y. What we've seen is the rule for parallel transport is v mu parallelly transported is equal to, for a small displacement, is equal to v mu minus Christoffel symbol mu nu rho, the displacement dx nu, and the old components v rho. Okay, so in Cartesian coordinates, all the Christoffel symbols are 0. So in Cartesian coordinates, it's saying that when I transport a vector from a point x to a point another point x prime, the components of v in the Cartesian basis will not change. Okay, that coincides with your intuitive notion of parallel transport of vectors in Cartesian space, right? The components of v do not change in this Cartesian coordinate system. However, if I take if I switch to polar coordinates, okay, then you'll find something interesting. We've seen in polar coordinates these gammas are non-zero. Okay, the parallel transport coefficients are non-zero. And now we think about our vector. So now if we think about this as x and y, remember that we can always think about the r hat and theta hat directions as being the same directions as this is really partial partial r, and this is 1 by r partial partial theta. This is the unit vector in this direction. And now if we write a vector, okay, but we expand it in terms of this partial partial theta and partial partial r, okay, so we write down a vector which is some vr partial partial r plus v theta partial partial theta. We will see that when I move to a different point, okay, infinitesimally far away, but a different point with, let's say, a different r hat and theta hat. Okay, the r hat and theta hat components of this vector, okay, after a displacement will be different from the original ones that I started with. Okay, intuitively, of course, you can understand that by the fact that your coordinate system, if I make this displacement, is rotated. Okay, since my coordinate system is rotated, it's easy to understand why this Vr prime and V theta prime will be some linear combination of the old Vr and the old V theta. Okay, the homework exercise that you should try out is to exactly work out what these new components Vr prime and V theta prime are in terms of the old Vr and V theta, and to convince yourself that basically the reason for the change is exactly because your coordinate system has rotated a little bit in this small displacement. Okay, so that basically shows why you have this kind of connection. So the vector is still the same. So when I parallelly transport it, it's kind of pointing in the same direction. So whatever this direction is the same direction here. These are parallel to each other. Okay, but because the coordinate system r hat and theta hat are rotated with respect to the original r hat and theta hat, the components of this vector have now changed. Okay, so parallel transport is working exactly the same way in Cartesian coordinates and polar coordinates. But when I try to figure out the components of vectors in the particular coordinate system, the transformation rule looks more complicated in polar coordinates. Okay, it looks like a rotation of the components. Okay, so this I'm not working out. Okay, but this you can try it out. Okay, as homework. Okay, and finally, let me do this last exercise of working out the geodesics. Okay, so this is the geodesic equation, which is basically starting from the point that if I have a curve, what is the straightest possible curve in this Euclidean space with metric 1, 1, 0, 0? Okay, so by definition, the curve was such that the tangent vectors to this curve are parallelly transported, and they don't change under parallel transport. That is, this is true for V being any tangent vector on this curve. Okay. In coordinates, we saw that the geodesic equation just works out to be this. So if this curve is parameterized by some x mu of t, okay, t is a parameter that describes where you are along the curve, then I can write the geodesic equation in this way. Okay, instead of t, because it's confusing to use t later when we use time. So sometimes people use lambda. Okay, it doesn't really matter, but here it doesn't matter. But later when we use, for example, space-time coordinates, okay, t will be one of our coordinates. Okay, and so you don't want to use t as a parameter for the trajectory. Okay, so so maybe later you want to switch this t to something like lambda. Okay, so now if I want to describe this curve, we've seen in coordinates it's d square x mu by d lambda square plus gamma mu nu lambda dx nu d lambda dx lambda d lambda. Okay. Okay, so lambda is problematic if you use an index lambda, but anyway, you have to choose some economization of your variables. Okay, so now in Cartesian coordinates, all the gammas are 0. Okay, in Cartesian coordinates, all the gammas are 0. So in Cartesian coordinates, we can easily work out what the geodesics are. So in Cartesian coordinates, we would get d square x by dt square is 0, or d square x by d lambda square is 0, and d square y by d lambda square is 0. Lambda is just a parameter. What we're really interested in is we want to eliminate that parameter and find the curve y as a function of x. Okay, or we can find the curve parametrically as y as a function of lambda and x as a function of lambda. So what is this curve? Well, you can solve this equation easily. So given some initial conditions, x is at plus b, y is some ct plus d. Okay, a, b, and c, d are some constants that have to be worked out. I mean, they would give you different curves which satisfy the same geodesic equation. So now if we eliminate the parameter t, okay, if we eliminate the parameter t, x is linear in t, y is linear in t, therefore x is linear in y, or y is linear in x. So the relationship between y and x will just be something like mx plus c, which is a straight line. So in Euclidean space, which is in R2, the curve which keeps tangent vectors parallel to itself is just a straight line, because the tangent vector here parallelly transported along this curve would look, sorry, this is probably the terrible straight line. Let me draw another one. Okay, so if I take the tangent vector to this curve here, I parallelly transport it along the curve here, then this parallelly transported tangent vector is also tangent to the curve here. So therefore, straight lines are really the geodesics, okay, in Euclidean space. In fact, they are the lines which actually minimize or extremize the distance between any 2 points. Okay, so it's the curve of minimum distance between any 2 points. That we've not shown, but it can also show that geodesics either minimize or maximize the distance between any 2 points. So geodesics are just straight lines. So and these constants tell me that any straight line, I can choose any straight line. Okay, and that's a perfectly valid choice, okay, of a geodesic. Okay, so given a metric, you can work out connection coefficients, which are Christoffel symbols, which are specific to that metric. Once you pick out those Christoffel symbols, you can find the geodesics, and the geodesics tell you the sort of straightest possible path given the metric that you have. The notion of a straight path requires you to already have the notion of a metric. Okay, you can do the same thing in polar coordinates. It's more complicated. In polar coordinates, you'll have these complicated equations because these Christoffel symbols are non-zero. Okay, so again, I've shared these notes with you. You can check this out as a homework exercise. So we have something like gamma r theta theta here in the d square r by d lambda square equation, something similar in the d square theta by d lambda square equation. So you'll get some complicated differential equations. Okay, these differential equations are harder to solve, but the solution will be exactly the same. Okay, the solution will be exactly the same, except this is now going to be expressed in terms of r theta coordinates. Okay, so for example, so we won't solve this, but if you have a curve which is, let's say, y is mx plus c, in polar coordinates, that same curve is r sine theta is m r cos theta plus c. Or in other words, it's this. Okay, it's r is equal 1 by r is sine theta minus m cos theta by some c prime by the c prime. So what this means is this curve, if I solve this equation and I find r as a function of lambda and theta as a function of lambda, and if I eliminated lambda, this is the equation that I would get, okay, which relates r and theta. So so you can find the geodesic in either set of coordinate system. It just becomes more complicated if you use a coordinate system, okay, which is not suited to the metric, okay. But in principle, it's possible to solve these differential equations. Probably there is a simple substitution that you can make to solve this. Okay, actually, the simplest substitution to solve these equations is to just switch back to Cartesian coordinates, right? To make this substitution. Okay, but maybe there's other ways to solve this the same differential equations. Okay. Yeah. Okay. So I'll probably leave this last thing here, which is just how to evaluate these covariant derivatives. Okay, the covariant derivatives we've already seen, they have to be evaluated using this connection. Okay, in particular, we're going to use the metric connection to evaluate those covariant derivatives. So in Cartesian coordinates, again, all these connections vanish. So these derivatives, del x v, the y component of this derivative is just your usual partial x vy. Okay, because these connection coefficients vanish. But in polar coordinates, this gets more complicated. Okay, so you can work out in polar coordinates, you'll have these extra contributions. Okay. Yeah, I think that's it. I'll stop here. Okay, and first I'll take questions about this. And if you have any other questions about the tutorial sheets, I'm happy to answer those as well. Any questions? They can be very basic. It's all right. I mean, the entire point of the tutorial is to teach you how to calculate using these ideas.
Sir,
Yeah, go ahead.
in the dual vectors related by isomorphism part,
Did I miss it here? Yeah, dual vectors related by isomorphism. Yeah.
I didn't how did we get these relations?
Oh, this one?
Yes, sir.
Yeah, so what we argued is in class we had shown that there's an isomorphism once you have a metric. Okay, so the argument was this, that once I have a metric, then a metric is a two form. Okay, which sorry, it's a 0-2 type tensor. Okay, so what it means is it takes two vectors as input and returns a real number. Okay,
Yes.
or on a manifold, it takes two vector fields as inputs and returns a scalar field or a real scalar function on the manifold.
Yes.
So G takes two vectors and returns a real number. If you now think about the action of G on one vector, okay, the action of G on one vector, and you ask, what is this? Okay, the action of G on one vector, what does it do? Okay, it takes in a vector. So it takes in a vector and it maps it to real numbers. But this is exactly what dual vectors do. They take in a vector and map it to real numbers.
Yes.
Okay, so we use this to define an isomorphism between any vector v given a metric G. There is an isomorphism between dual vectors and vectors. Okay, and basically the isomorphism is that the dual vector is, you can think of symbolically like this. In components, it's this relationship here. Okay, in components, basically, yeah, you can go back and look at the notes where we talked about these dual vectors.
Yes. Okay.
Any other questions?
Hello, sir.
Yeah, hi Toshi.
Sir, I have a question like regarding this. Like you gave one homework exercise to show that for a vector there is a unique dual vector.
Given a metric.
Yes, sir. Given a metric. Like, yeah. So, sir, like like I've tried it this way that like if we take two vectors using the symmetry property of the metric, like GUV is equal to GVU, and so like and expressing GU as some WU and GV as WV. So if we get WUV is equal to WVU.
Sorry, it's not possible for me to follow. Just saying it. Let me just write down what you're saying.
Oh yes, yes.
So say that again.
So like G acting on UV is equal to G acting on VU.
Yes.
And now I've written G acting on U with one slot open as WU.
As WU.
Yes, and for V, similarly for V, WV. Yes. So now if like if W now using the now if WU is equal to WV, and before that WU acting on V is equal to WV acting on U from the symmetry property.
WU acting on V. Yeah.
Yes. Now if WU is equal to WV.
If WU equals WV.
Yes. Then like WU acting on V minus U is equal to 0.
WU acting on V minus U is equal to 0. Yes, for all V's and U's.
Yes, like from this statement this holds. So and now similarly, well, like we can also write W as WV. So so now we can write this as G of U comma V minus U is equal to 0. Right. Yes, sir. And now like we can also write this WU as WV. So this will also hold like WV acting on V minus U is equal to 0.
Sorry, slow down. WU as?
No, like we can write WU as WV as well. So,
yeah, and so that would give you GV U minus V is 0.
Yes, sir. So from the second axiom, this it holds that V minus U is equal to 0.
That if this is true for any V and U, then this vector itself is 0, which means V is equal to U.
Yes. So is this a proof? Like?
Yeah, I think that's the proof.
Okay. Sir.
Yeah, and I'm glad you showed it this way, because basically the point is that I mean, these objects are coordinate independent, okay? And often it's convenient to think about them in terms of coordinates, but really the properties of these objects that we've defined are independent of coordinates, okay? Like the existence of vectors. Okay, any other coordinates? Any other questions? Yeah, Shashwat, sorry, you were not audible.
Hello.
Yeah, Khagesh, go ahead.
Hello, sir. Am I audible now?
Yeah.
Yes, sir. This is Shashwat, sir.
Okay, yeah, go ahead.
So I have a doubt related to one of the assignment 2 problems. So basically, in the for example, in the if you consider the manifold to be R3, and suppose a vector is being like, for example, we transport a vector from one point to another. We try to do it parallelly, and suppose the magnitude of that vector changes. So, do we still call it parallelly transported? I mean, is it allowed?
Suppose the magnitude changes.
Is it allowed?
No, okay. So again, so our usual notion of parallel transport, right, in 3 dimensions or 2 dimensions, is we have a notion of what it means for the vector to remain parallel to itself, right? That is our usual notion. Okay. This usual notion is based on the choice of metric. The choice of metric gives you a unique connection, which is the Christoffel symbol.
Yes.
Okay. And in that unique Christoffel symbol, the magnitude of the vector does not change with this particular choice of metric.
Yes, sir. Right. So in one of the questions, actually, it was stated that we are supposed to show that a particular vector, like a particular vector field, gets parallelly transported along a particular curve. But the thing was, when I was trying to like, it should have satisfied the parallel transport condition, but the magnitude of the vector was changing. That's why on the RHS, instead of 0, I was getting some constant.
Magnitude of the vector will change. Oh, sorry. See, the thing about parallel transport is if I transport a vector, so what is the rule for parallel transport? I have a vector u. I want to parallelly transport it along this curve where the tangent vectors to this curve are v. Okay. Now remember that the inner product of u and v, this has to be preserved along the curve. This should not change under parallel transport. Right? So if the tangent vector to the curve has changed as I move to a different point, then u itself will change as I move to it. I mean, the magnitude, sorry, you can imagine that if the magnitude of v changes as I move along the curve, then the magnitude of u will also change as I move along the curve to keep this inner product the same. But this is the only restriction.
Yes,
okay, the magnitude of the vector can change in parallel transport.
Okay, but the problem is, anyways, like the parallel transport equation that should get satisfied, right? The parallel transport condition.
What is the parallel transport condition? Sorry, what condition are you saying is not satisfied?
What I'm saying is that like the condition we got from like nabla w with respect to v, that is
Nabla, yeah. So this would be this.
Yes, sir. This should be 0, right?
Yeah.
Yes. So for one of the in one of the questions, I was getting instead of 0, I was getting some constant. But
okay. So let me just tell you this. Okay. So there is, if you had done one of the earlier problems in the tutorial sheet, I think problem 3, you'll show that you can actually relax this condition. Okay. To be that this should just be parallel to u.
Got it. Yes, sir.
Okay. So this is too strict a condition. You can get this, but you can always show that it's always possible to do a reparameterization of the curve such that the geodesic equation doesn't have this right hand side. Okay, but you have to relate it t prime, the parameter t prime to t.
Yes, sir. Got it. Thank you.
Okay, other questions?
Sir, are we allowed to make a formula sheet?
Yeah, I'll just decide either it'll either be formula sheet or open notes or something, right? I mean, you won't have to memorize this formula.
Yeah.
Okay, and I'll give you enough time. Like I'll give you at least a day to make the formula sheet. So.
All right, sir. Thank you.
Sir, you just said that the magnitude of a vector can change when we parallelly transport it. But sir, don't we define the magnitude of vector as the inner product of the vector with itself?
Yes.
And sir, we are taking the connection which preserves the norm of a vector, so of two vectors. So the norm should be preserved, right? So this implies that the magnitude should remain same.
Oh, yeah, thanks for that. So if we have two vectors, yeah, sorry, thanks for that. If I have a vector u and a vector, sorry, and just a vector u, then yeah, sorry, the metric connection so under a general connection. Sorry, okay, I take that back what I said earlier. Thanks for that. Sorry, this was not this is not what I meant to say. Okay, and let me just clarify what. So two things. So one is first, what is parallel transport? So parallel transport itself in general is defined as long as I specify connection. The connection need not be a metric connection. For a general connection, okay, it gives me a prescription for how to transport u along some curve with tangent vectors v. Okay, and in particular, u satisfies this equation. Grad v of u is 0, or as we discussed, it can be written as at least it's parallel to u. Okay, that's, you can extend the definition to say that the change in the vector under parallel transport is parallel to the original vector. Okay, if it is parallel to the original vector under transport, so the only thing is that it has to be parallel. Okay, this is the only rule that we demand. Now, if we go to a metric connection, okay, so at this stage there's no notion of magnitude because we don't have a metric. Now, if we go to a metric connection, by definition, we're saying that if I have two vectors u and v, and I parallelly transport, sorry, u and w, and I parallelly transport them along this curve, that is, u satisfies this some equation like this, f u, and v satisfies some equation like this, sorry, grad v w equals g. Yeah, okay, so there was an assumption. Let me tell you what that assumption is. Okay, I think this will make it clear. So if you, so what we had assumed was that the vectors u and v actually we had chosen the parameter along the curve. Okay, so that is when you choose the parameter along the curve, that changes the tangent vectors to the curve. Okay, because you're traveling, the tangent vector, if you remember, had coefficients dx mu dt, partial x mu. If you change the parameter along the curve, okay, to switch to what is called the canonical choice, okay, in the canonical choice, you can choose this vector v, or equivalently choose this parameter t, such that this is satisfied. Okay, so if you make the canonical choice, this is satisfied. And with this canonical choice, that's how we derive the Christoffel symbols. The Christoffel symbols were derived for this canonical choice. Because if you recall the derivation, we said that under parallel transport, the inner product, which is G acting on UW, this is preserved. Okay, and what we did was we took this plus grad V U. Okay, so this is just the Leibniz rule, right? I'm just writing it schematically. Grad V W U. Okay, and we said that this is 0, and then we use that to get an equation for, and we said this is true for any components of U and W, and therefore we were able to get a relationship. This derivative depends on the connection coefficients, and we use that to derive the connection coefficients in terms of G. Okay, so this is G upper mu rho partial G minus partial G, right? So we had some equation like this. This gives the Christoffel symbols. So the important thing was that the norms of the vectors under parallel transport are preserved, okay, was under the assumption that you have chosen a canonical parameterization for Yeah, for the trajectories, actually. Yeah, so for a single trajectory, it is always possible to choose a parameterization such that this is true. Okay, and if you switch to that parameterization and you do the parallel transport in that parameterization, then the norm of the vector will not change. If you change your parameterization, then the norm of the vector changes by a simple scaling factor, okay, which will be basically dt over dt prime. Okay, this will be the extra scaling that you get under transport. So basically, I'm going to do, this is now, instead of sorry.
Sir, here like changing the parameterization should not affect the norm conservation property, right? Because the when we are assuming that the norm should be conserved, using that assumption, we are determining the Christoffel symbols. But changing the parameter just affects that proportionality factor f. So no, I think norm should still be preserved if we are using the Christoffel symbols determined by the connection is the metric connection.
No, because basically this term would be non-zero. It would be f times u if you use the uh, non-canonical choice, or the okay. So sorry, that choice for parameterization t. Okay, so let's say if I want to make this equation, I want to put it in this form, then there is a reparameterization that I can do that will ensure this. Okay. But if I want to put this in this form, there's a different reparameterization that I need to do to put it in this form. Okay, so now since we only have one vector, okay, there is always exists a reparameterization that I can do to put it in this form. Okay, but it's not guaranteed that that your parameterization is such that you are.
Sir,
Yeah.
sir, when del nu minus f, can we, I mean, uh, construct it as a covariant derivative by redefining our connection?
You want to construct this as your covariant derivative?
Some delta mu nu.
This doesn't satisfy any of the properties that we want for a connection. Okay, I mean, we had some properties that we require, right? For example, it should be, if I scale v by some amount, right, then the whole thing should scale with g, right? And obviously that will not be satisfied for arbitrary f.
Okay.
Um, Yeah, so no, Prakhar, I don't think it's obvious that, in fact, I don't think it'll be true in general. The Christoffel symbol was derived under the assumption that this is true for an arbitrary vector. Okay, so if this is true, then you've chosen the canonical parameterization. And for this particular vector, you have chosen the canonical parameterization. And under that assumption, the magnitude of this vector will not change under parallel transport. So if you fix your parameterization, okay, and if your parameterization is non-canonical, then you will have this. And the equation that we started with, right, which is to assume that this is zero, and you know the Christoffel symbols will be worked out. We'll have some extra term in there, right, which basically will be that which will tell us that the norm is not conserved. Okay, along the flow. So it's only under this canonical parameterization that that the norm of the vector will be conserved. So indeed, that's precisely the point. This statement of this is essentially saying that when I transport the vector, it is the only constraint is it's parallel to itself. If it's zero, you're saying there's no change in the vector. If it's parallel to itself, that means that the magnitude can change. Okay, and it's still parallel to itself. Okay, but there is a choice of Sorry, what is the correct statement? No, sorry. The correct statement is this. Okay, this is the right generalization of parallel transport. Okay, this is a coordinate independent statement. Okay. So under parallel transport, it is possible to do this. This is the only correct statement of which is coordinate invariant. The fact that you can put it in the other form by a reparametrization is a coordinate dependent statement. The fact that you can write it in this form by a change of coordinates, this is a coordinate dependent statement. Okay, it doesn't mean that you are saying grad VU is 0 by a change of coordinates or by change of parameterization. Or is it? If I change my parameterization, I'm changing my tangent vectors. Yeah, so I'm changing a tangent vector V prime. Okay, yeah, so by thinking about how fast I'm moving along this curve, okay, I could be tracing the same points but moving at a different rate. Okay, and that would change my tangent vectors. So there's a tangent vector V prime that I can choose. Okay, which in some sense, remember that these curves, right, are really, you can think of a family of curves which are all going through. No, sorry, never mind. There are different V primes, okay, that you can have at each point. Okay, the tangent vectors can change, which is the magnitude of the tangent vector is changing, which means even though I'm following the same points, you're sort of following them at a different rate. So only with this choice, okay, with this particular rate where the change in U is 0, in that particular case, it will be that that the magnitude of U does not change in the parallel transport. In general, the magnitude of U will change. Do you, I mean, does this make sense, Prakhar?
Yes, sir. Sir, so finally, we are concluding that that if you are not using the canonical transformations, or sorry, the canonical parameterization, then the norm would change, right?
Yeah.
Yeah, okay. Yes, sir. It's clear.
Okay, any last questions? Okay, I think we can stop here. Okay, so I'll send instructions for the midsem, and yeah, I'll see you all on Monday, either online or in the classroom. Okay, see you then. Bye-bye.
Thank you, sir.